Welcome to CPE605 Mathematical Modeling in Computer Engineering. This is the backup lecture of the fourth lecture, Modeling System Dynamics. My name is Prom-on. I am the instructor of this course. Let's begin. In this lecture, we will discuss the situation that there are two or more populations that need to be considered together, and they have certain effects on one another. These populations can be thought of as not just populations in the strict sense. It can be thought of as something like the states, dependent variables. Such situation can be found when there are something like this. We can think of the number of cars in each intersection as one variable, and the change of the number of cars in each intersection would affect the number of the car in another intersection. So we can model the traffic congestion that occur using these representations of the change of two variables, which one variable affects the change of another variable. We can also find such interaction in the closer context, like in computer network. This figure shows the hypothetical configuration of hosts and routers in the general network, and the internet package that transfer between these hosts and routers can be thought of as populations, and the change of the amount of traffic would from one router to the host or to another router. That is, we can use a set of differential equations. Each represents the change of each population to describe this whole network, and we are able to solve for the trends of this change of these populations to see what will happen if something happens to node in the network, or there are more data flowing into the network. Interaction can be found in the real-world context, like economics. The change of the oil price and the change of oil reserve interact with one another. If the oil price drops, people would go to fill in the tanks more often, and the amount of oil reserve would significantly dropping. If the oil price increased, then the oil reserve would be also increased due to people not going to fill in their tanks. On the other hand, if the oil reserve drop, the oil price would increase significantly due to the supply-demand balance. And if the oil reserve increase, then the increase in supply would decrease the oil price. Interaction can be found in the ecology, like the actual population change between the predator species and the prey species. The increase of the prey species would result in the increase of the predator species as well, and the decrease of prey would decrease the number of predators. Meanwhile, the increase of the predator would reduce the number of the prey, and the decrease of the predator would increase the number of the prey. So the change of one population affects another population. We can also use this type of model to model the climate change. If we represent the amount of heat of each continent as one variable, the transfer of the heat from one continent to another would create a phenomenon that is actually observed in real life, like El Nino or La Nina. All of the models that we mentioned relies on the effects of one variable to the change of another variable. So let's suppose that we have two populations, the simplest case, xt and yt, which denote the number of the members in those populations. We will usually omit t to simplify the equations. If we are talking about a change of one population that depends only on the current size of its own population, then for the dx by dt, it would rely only on some constant in x, meaning that the change of x would rely only on x and x alone, and the change of y would rely on the number of y alone. But if the change of one population depends not just on the size of its own population, but also on the size of another population, then we would have a system looks like an equation look like this. That is, the change relies on its own population and also relies on the size of another population as well. And the change of another population also relies on the x population and its own population. We will talk about this case in this week. And in the next week, we will talk about what will happen if there is interaction between the two populations. If we have n population, we could write the change of each population as differential equations. And when we combine all of the equations together, it would form the linear system, the system of linear equations. Let's look at each of these one by one. The first equation describes the change of the variable x1. It describes the change equaling to a coefficient multiplied by the population x1, coefficient, another coefficient multiplied the population x2, and so on until the coefficient multiplied by the population xn, plus some function f1, which is something like the external forcing function that is applied to the population x1. And x2 also have the similar form, but has its own coefficients and its own external forcing function. And this applies to all cases until the population xn. We refer to a system like this a linear system. Like in one variable differential equation, the equation can be homogeneous or non-homogeneous. If the external force equals 0, then the linear system is homogeneous, which making the solution of the system contains only the general solution or the natural response. You may also know the term as the transient response. But if ft is not 0, then you have a non-homogeneous system, which creates a situation that the solution of the system contains both general and particular solution, both the natural and forced responses. We will first consider the case that the system are homogeneous system, and later looking at the case of the non-homogeneous system. The linear system can be written in the form of matrix. If we let the matrix X to denote a vector of population size x1 to xn, and the matrix A represents the coefficients of the linear system. The matrix F represents the vector of external forces applying to each population. Then we can write the linear system as d by dt of the vector x equals A, the matrix A, multiply the vector x plus f. Or simply x prime equals ax plus f. For a homogeneous system, the matrix would be simply x prime equals ax. This first example shows you that you can represent a linear system in the matrix form. This system, dx by dt equals 3x plus y plus 4y, and dy by dt equals 5x minus 7y, can be written as x prime equals the matrix A is 3, 4, 5, minus 7, and x, where x is a vector of x and y. The usual question when you form a linear system would be to identify the closed form of the populations or the formula of each population. Knowing that formula, you'll be able to project the size of the population at any times. We call that closed form a solution vector of the system. That solution vector is actually the vector x. This vector x consists of the population x1 to xn. Each is differentiable function satisfying the linear system. Let's look at the second example. For an interval from -infinity to infinity, we can verify that this x1 and this x2 are the solutions of the system x prime equals 1353x. We can verify this by applying a solution vector x and substitute x1 to this and see if both sides hold, and also doing the same thing for x2. Testing the first vector by substitute x1 into the equation. d e to the minus 2t and minus e to the minus 2t equals minus 2 e to the minus 2t, and minus 2 times minus 1 is 2 e to the minus 2t. The matrix multiplication in the right hand side yield the first row and the first column e to the minus 2t minus 3 e to the minus 2t equaling minus 2 e to the minus 2t, and 5 e to the minus 2t minus 3 e to the minus 2t equaling to 2 e to the minus 2t. The left hand side equals the right hand side, so this verifies that the first vector is the solution vector of the system. For the second vector, 3e to the 60 and 5e to the 60, the derivative of this equals 18e to the minus 2t minus 60. The derivative of this equals to 18 e to the minus e to the 60 and 30 e to the 60. The matrix multiplication also yield the same vector, which verifies that the second vector is also the solution vector of this system. Let's say that you have a set of solution vectors x1 to xk of the homogeneous system on interval I. Then the linear combination of these vectors is also a solution of the system. C1 to ck are arbitrary constants multiplying these solution vectors. The reason that this superposition principle holds is because the system we have is a linear system. In a linear system, applying individual inputs to the system equals to applying the combination of inputs to the systems. So the solution of the systems also rely on the same principle. That is, if you have a set of solutions, the combination of these solutions would also be a solution of the system. Let's further looking at the relationship between the solution vectors. If you have x1 to xk being a set of solution vectors of the homogeneous system, then we say that the set is linearly dependent if when you combine them together, and it can be equaling to 0, meaning that you can represent one vector as a superpositional sum of another vectors. If it can be derived in that way, then that set of solution vector is linearly dependent. On the other hand, if the set of vectors cannot be scaled and combined to be zero, then that set is linearly independent. If you have a set of linearly independent solution vectors x1 to xn of the homogeneous system, these linearly independent solution vectors is a fundamental set solution of the system. Being a fundamental set of solution, meaning that the final solution of the system would be represented in the form of these vectors. And if x1 to xn are in a fundamental set of solutions of a homogeneous system, then we can create a general solution of the system by linearly combining the solution vectors in the fundamental set together and scale them by the coefficient c1 to cn. For examples, given that x1 and x2, which are tested earlier in the previous example, as linearly independent solutions of these systems. This system is a system describing the change of two populations. That means we would have two solution vectors associated with the order of the system. And since x1 and x2 are linearly independent solutions, we can write a general solution of the system in the form of c1x1 plus c2x2 equals c1 and x1 and plus c2 and x2. A particular solution for a non-homogeneous system can be found by assuming that the particular solution is in the same form of the function ft, and then test that assumption by substitute xp into the linear system. The solution of a non-homogeneous system would then be the combination between the general solution and the particular solution. From a one-variable ordinary differential equation, the equation we solved last time, we observed that the solution of homogeneous system is often in the form of exponential terms. So for a homogeneous system with n linear differential equations, the solution of the system can be in the form of a vector from k1 to kn, and the exponential term, we will write this vector k associated with e to the lambda t. For a homogeneous system, x prime equals ax, if we substitute x equal k e to the lambda t to the system, we will have this equation k lambda e to the lambda t, the differentiation of k e to the lambda t, equals a k e to the lambda t. Dividing e to the lambda t out, we will have ak equals lambda k. Moving this part to the left hand side and pulling a and lambda. For this equation to hold, there are two possibilities. First, this part must be 0 or k must be 0. However, when k is 0, it means that the vectors of solution would be all 0, which is a trivial case. For the non-trivial case, then a minus lambda I has to be equal to 0. And for that, it requires that the determinant of a minus lambda I equals 0. From this determinant, we will find a polynomial of equations of lambda, which is often called a characteristic equation of the matrix A. The solutions of this polynomial equation are the eigenvalues of A. And the solution k, which is not zero, of a minus lambda I k equals 0, correspond to an eigenvalue lambda is called an eigenvector of A. And each k corresponds to an eigenvalue lambda. The eigenvalues can take three possible forms. They can be distinct and real eigenvalues, repeated eigenvalues, or complex eigenvalues. We will look at these three different forms of eigenvalues and determine how that affects the form of the general solutions. In the first case, where the eigenvalues are distinct and real, let lambda 1 to lambda n be the n distinct real eigenvalues we found from the matrix A of the homogeneous system, and let k1 to kn be the corresponding eigenvectors of lambda 1 to lambda n. The general solution of the system would be in this form. That is, it is the summation of the coefficient of that terms multiplying the eigenvector of that eigenvalue. Let's look at this fourth example when we have distinct and real eigenvalues. In IT market, the sale volumes of personal computer, we use X to denote the population, and the UPS, an uninterrupted power supply, we use Y to represent that population, have certain relationship which can be expressed in this linear system. To determine the general solution of this system, we will first determine the eigenvalues of the system. For that, this a minus lambda I has to equal 0, so the determinant of this has to equal 0. The determinant of this is the multiplication between 2 minus lambda, 1 minus lambda, and minus multiplying up minus 2 times 3. And this is lambda square minus 3 lambda from this and this minus 4. This is minus 6 plus 2 equals minus 4. Factoring this polynomial, we have lambda minus 4 times lambda plus 1. That is lambda equals minus 1 and 4. These are real and distinct eigenvalues. So we will then determine eigenvector corresponding to each of these eigenvalues. We will first substitute the lambda into this equation, a minus lambda I k equals 0. So we have this is 2 minus 1, which is plus 1. This is 3 and 3 and k1 and k2. So multiplying this, we have 3k1 plus 3k2 equals 0. That is k2 equals minus k1. So if we let k1 equal 0, k1 equal 1, then k2 would equal minus 1. Then we have the x1, which is the eigenvector, and e to the eigenvalue minus e to the minus t. If lambda equals 4, then we will have 2 minus 4 and 3, 2 and 1 minus 4. And this is minus 2 and 3. Multiplying the first row to this column, we have minus 2k1 plus 3k2 equals 0, meaning that k2 equals 2 over 3k1. If we let k1 equals 3, then k2 would equals 2. Then we have the eigenvector 3, 2 correspond to the eigenvalue 4. So the general solution would be in the form of c1 x1 plus c2 x2, with c1 and the x1 plus c2 and the x2. c1 and c2 are usually determined from the initial condition. Suppose we found that c1 and c2 are equal to 1. We can plot the change of the population of x and y population like this, that x population will goes down and goes up, and the one population will always go up like this. Plotting them on the same plane, we create something called phase plane. This is very similar to the phase line we discussed last time. Phase plane will indicate the trajectory or the change of the populations when we plot them together. This plot tells us that the change of x here, when considering together with the change of y, will have a point that is a kind of a pivot point that x change the direction. If we iterate the value of c for the multiple value of c, we will create a phase portrait which tells us the change of the system when we have different initial conditions, which results in different values of c. In the last slide, our system starting from somewhere around this, so it goes up to the upper left and then turn to the upper right. The center point here of this system is an equilibrium of the system. This type of equilibrium is called a repeller. In the second case, then we would have m linearly independent solutions. The first one is like in the first case k11 e to the lambda 1 t. The second one would be k multiplied by t e to the lambda 1 t plus another k multiplying by e to the lambda 1 t, and so on. The pattern would be km1 e to the m-1 over m-1 factorial e to the lambda 1 t, and km2 t to the m-2 over m-2 factorial e to the lambda 2 t, and so on until kmm e to the lambda 1 t. Note that these kij are column vectors which need to be determined. Let's consider a simple situation when we have eigenvalue of multiple of 2. Let lambda 1 be that eigenvalue that is of multiples of 2, and there is only one eigenvector associated with this value. The second solution can be found in this form, where k is one vector and p is another vector. If we substitute the second solution into the system and arrange the equations, we would have this form. That is, for this equation to hold, this part must equal 0, and this part must also equal 0. So we have two equations, a minus lambda 1i k equals 0, just like in the previous case, and a minus lambda 1i times p equals k. So we need to first determine k here and determine p later to determine the second solution. The steps to solve this would be to first determine the first solution x1, and then we can solve for the second solution, which will lead us to x2. Then we can find the general solution by combining the two solutions together with arbitrary constants c1 and c2 multiplying the corresponding x1 and x2. Let's consider this fifth example of repeated eigenvalues. Let's say that we have a thermal control system that designed for this server room. The server cluster generates heat to the server room, and the air conditioning system dissipates heat from the room. let's say that X represents the heat generated in the room and Y is the heat at the air conditioning system. We can describe this system as this linear system. That is dx by dt equals 3x, the heat generated by the server cluster, minus 18y, the conducting of the heat out, the dissipation of the heat, and dy by dt equals 2x, the influence from x, and minus 9y, the dissipation of the heat of y. To find the general solution of this system, we still need to first determine the eigenvalues. So the determinant of A minus lambda I must equal 0. Then we have lambda equals both minus 3. So to determine the fundamental set, we need to first consider each case. We need to first consider the case when eigenvector lambda equals minus 3. When lambda equals minus 3, we have putting minus 3 here. Then we have 6 k1 minus 18 k2 equals 0, which is k1 equals 3 k2. So if we set k1 to 1, so if we set k2 to 1, then k1 would be 3, which will make us having this x1 equals 3,1 and e to the minus 3t. Now for the second solution of lambda equals minus 3. Substitute minus 3 to lambda here. We have this as 6. This is minus 12. And P1 and P2. The right hand side would be the K, the eigenvector from the previous slide. Then we would have, by multiplying the first row with this column, we will have 6P1 minus 18P2 equals 3, or P1 equals 1 plus 3P2 over 2. If we set P2 now to 0, you can see that we can set P2 to 0 now, because it doesn't make the solution to be trivial solution. We will get P1 equals 1 over 2. So this x2 would be 3,1 t e to the minus 3t plus 1 over 2 and 0 e to the minus 3t. Combining x1 and x2 together, we will have the general solution in the form of c1 and the first x1 and c2 x2. If in the simple case c1 and c2 are 1, then we will have a trajectory like this, starting from this point and then moving along this line and reaching this point. If we try on different initial conditions, we will have a phase portrait like this. That is, no matter where you start, it will always approach this point. This point is an equilibrium of the system. The behavior of the system tells us that this type of equilibrium attracts the solutions no matter where you start. So it is often called an attractor. Now the last case, when we have complex eigenvalues, we can do this in the same way that we did in the first case, but instead of having real values, we would have a complex eigenvalue. Lambda 1 equals alpha plus I beta instead. And having one solution in the complex form, we would have another solution if the system has more than the order of 2 in the conjugate form of the first solution. We need to rely on the Euler relation in order to solve for the closed form of the complex eigenvalues. Let's look at this example, the example number 6. If we have the system and the initial condition like this, let's look at how can we determine the general solution or the solution of the system from that, because the system is homogeneous. We need to first determine eigenvalues of the system. The eigenvalues of the systems are plus and minus 2i. This is a complex number, only containing the imaginary number. So let's consider the case where eigenvalues lambda equals 2i. If lambda equals 2i, we will have 2i here and 2i here. Multiplying, let's say, this row to this column, we will have minus k1 plus minus 2 minus 2i k2, which means that k1 equals minus 2 minus 2i k2. If we let k2 equals minus 1, then k1 would be 2 plus 2i. Then we would have the matrix, the solution vector x1 equaling to 2 plus 2i and minus 1 e to the I 2t. This vector is actually the real part and the imaginary part, and for this complex exponential, it is the cosine 2t plus I sine 2t. Multiplying two terms together, we have 2 and minus 1 cosine 2t, and I multiply I equals minus 1 and 2 0 and sine 2t, and the latter part also from multiplication. x2 would be the conjugate of x1, so you just need to change the sign here. And xc, the general solution, is the combined solutions of x1 and x2. Combining x1 and x2 and multiply x1 with c1, x2 with c2, we'd have this c1 multiplying x1 and c2 multiplying x2. So we would have this c1 plus c2, the first term c1i minus c2i, and the second term, and because these two are actually some constant, so we can represent it as another numbers, a1 and a2. Now what we need to do is to determine the values of a1 and a2 from initial condition. We know that x0 equals the vector of 2 and minus 1. So this is 2 and minus 1, and substitute 0 to value of t. We will have 2 and minus 1 and a 2 minus 1 plus a2 2 and 0, which means that we have two equations, 2a1 plus 2a2 equal to from the first row, and minus 1 equals minus a1, which means a1 equal 1 and a2 equals 0. So xc would be just this term, just like in the solution. This solution is the red line. It forms a cycle in the phase portrait. It means that if you have complex eigenvalues, the solution of the system will always circling around the center point, which is an equilibrium of the system. For non-homogeneous linear system, the system is in the forms of x prime equals ax plus f. We need to determine not just a general solution, but also the particular solution as well before determining the coefficient of the general solution. The step would be like this. You need to first solve for the form of xc, then solve for xp, then combine the solution together and then solve for the remaining unknown coefficients from the initial condition. Let's look at this example. This example shows you the system of two tanks, the models of two tanks. The first tank has an ethanol solution flowing into the first tank of which has the volume of 500 meters. The second tank has the volume of 100 meters. At time t equals 0, the tank A contains 500 liters of liquid, 200 of which are ethanol. Tank B contains 100 liters of liquid, which 7 of which are ethanol. And 3 liters of 20% ethanol solution are added to tank A per minute, and 5 liters flowing into tank B from tank A, 2 liters flowing from tank B back to tank A, and 3 liters flowing out of tank B. We can write this system as this differential equation. These differential equations are written from simple concept that the rate of change equal input rate minus output rate. So the change of the first tank, the solution, I forgot to mention that P and Q denote the number of liters of ethanol in tank A and B at time t. So dP by dt would be the amount of ethanol in the tank A. The amount of ethanol in the tank A would equals the input rate, which is from the external here 3 times 20% ethanol, and minus the flow from tank A to tank B minus 5 P over 500, the density of ethanol solution, plus 2 liters flowing into tank A from tank B, which is Q over 100, the density of ethanol in tank B. The change of Q equals the flowing in 5P over 500 and the flowing out, which composes of the flowing into tank A and the flowing out of tank B here in this part. So in total it is minus 5 Q over 100. Then this system would be a non-homogeneous system because we have F equals 0.6 and 0. So we need to determine, to determine the solution, we need to first determine the general solution of the system, then the particular solution. Let's look at first the general solution. Solving for the lambda, we have lambda equals minus 0.055 and minus 0.005. These are two real and distinct eigenvalues. So we need to consider the case where lambda equals minus 0.055, and for this value we have the relationship between K1, K2 and K1 like this. So we got the eigenvector correspond to these eigenvalues equals 1 and minus 2. In the case of lambda equals minus 0.005, we have the eigenvector corresponding to that eigenvalue like this. These are the same processes that we did earlier in the first case. The form of the general solution would be the first eigenvector e to the minus 0.055t and C2, the second eigenvector and the second eigenvalue. Then we will leave it as this, and then next to calculate the particular solution xp. Because elements in F are all constant, we would assume that the particular solution is also in the same form as F. So the particular solution contains constant A and B. If we substitute this a and b into the equation, x prime here will be 0 because the derivative of constant would equal 0. Then we would have only ax plus f. This is ax moving into the left hand side and f. Solving this system of equation can be done in different way. I use Cramer rules. I found that a equals 100 and b equals 20. Then we can combine the xc and xp together and getting this final form of solutions. Only two unknowns are c1 and c2, which can be determined from the initial condition. We have initial condition x0 equals 207. Substitute 207 to the left hand side and 0 to the right hand side. Then we have this equation, which consists of these two equations. Solving the two equations, we have c1 equals 16.9 and c2 equals 20.8. And plugging these two constants into the equation, we have the final solution pt and qt in this form. By assuming that t starts from 0 and so on, we can plot the change of the two populations to see the change in the amount of ethanol in each tank. You can see that the amount of ethanol dropped in the first tank to around 100, and in the second tank peak around this point and then drop. So with this behavior, we will be able to determine the point that the amount of alcohol exceeds the final solution. And actually we can also determine the rate of change here and seeing different type of behaviors. Plotting them in phase plane, we will see that starting from t equals 0, it starts from around this point and then moving to this point, which is an equilibrium of the system. This is the end of the lecture. If you have any questions, please feel free to ask me in our Facebook group. Bye.